Hi there, and thanks so much for joining me for this video. This video is going to begin Module 11, and it's kind of exciting because Module 11 is our final module. So we're going to be talking about our last two statistical tests that you guys are going to learn about in this course. So for this particular video, I'm going to talk about a statistical test known as an independent t-test. And whenever we conduct an independent t-test, we're going to be comparing two different groups in our sample on the same continuous outcome variable. So let's go ahead and jump right into it. All right, so the last statistical test that we talked about in Module 10 was a two-way chi-square test, right? And with the two-way chi-square test, essentially what we're trying to determine is if there is a relationship between two variables, both of which are categorical, right? So is there a relationship between gender and likelihood to conform, right? That's the example that we went through in lab last week. Or is there a relationship between introversion and extroversion and likelihood of smoking, right? So with the first example, we have one categorical variable of gender, and we have two levels, which are male and female. And for the second variable, we have likelihood to conform, yes or no. And in the second example, we have extroversion or introversion. That's our personality variable, which is one categorical variable. And then we have I forget the outcome variable that I just gave you, but whether we were looking at extroversion. Oh, that was it. Likelihood of smoking is one variable, yes or no, and extroversion and introversion is our second variable, right? So essentially what we learn when we conduct a two-way chi-square test is we're trying to find out if the observed frequencies or percentages in one group in our sample differ from the observed frequencies in another group from our sample, okay? So for example, if we found that males have a 67% or 67% of males in our sample conform, while only 78% of our females in our sample conform, right? The t-test or the two-way chi-square test would tell us whether that was a significant difference or not. Okay, so that's a two-way chi-square test. And in fact, what we're doing when we conduct an independent t-test is very, very similar. So again, in an independent t-test, we are comparing two separate groups in our sample to see if they are significantly different from each other. And one of our variables is going to be a categorical variable, but critically, with the independent t-test, our second variable, our outcome variable, is going to be continuous. Okay, so for example, if we wanted to compare math ability of males and females, right? Then our first variable would obviously be gender, males or females, and our second variable would be SAT score, which is a continuous variable. Okay, so essentially what we're doing is we're comparing two different groups of people in our sample on the same outcome measure, which is always continuous. Okay, so because we're comparing two different groups of people on the same outcome variable, the independent t-test is sometimes called a between subjects t-test, because again, we're making comparisons between the people in group A and the people in group B, or we're making comparisons between two different subsets of people in our sample. Okay, so again, what are some situations in which we might use an independent t-test? Well, situations where we'd want to compare two different groups that might already differ in some way, right? So this would be a situation where we are conducting a quasi-experimental study, and our outcome variable is continuous, right? So for example, if we wanted to compare the SAT scores of Mercer and Middle Georgia State students, right? So let's suppose we hypothesized that Mercer students have higher SAT scores than Middle Georgia State students, right? So one variable in this case is college or university, and there are two levels, Mercer and MGS. And our other variable, our outcome, our dependent variable that we're looking at is continuous, right? Because it's a score, it's a number, so it's a continuous variable, okay? Similarly, maybe we're looking for gender differences in typing speed, right? So again, we have one categorical variable that we are, in this case, it's again a quasi-experimental variable. So our independent variable, or our quasi-independent variable, is gender, male, female. And our dependent variable that we're looking at is typing speed, which is again a number. Maybe I don't know what a good typing speed would be. 100 words per minute, right? That's inherently quantitative. Okay, so whenever we conduct a quasi-experimental study with a quasi-independent variable looking at a continuous outcome, that would be a situation, or a continuous dependent variable, that would be a situation where we would want to conduct an independent t. Another scenario in which we would want to conduct an independent t-test is if we're comparing a treatment group to a control group, right? So let's suppose that we are trying to evaluate the effectiveness of an SAT prep course, right? So if we wanted to know if people who took the SAT prep course scored higher on the SAT than those that didn't, right? Again, we have a categorical variable, which is in this case the variable that's manipulated, right? So we have individuals that either took the prep course or individuals that didn't take the prep course. And then we're comparing them on a continuous dependent variable, which is their SAT score. Okay. Similarly, we might look at the effectiveness of a particular medication. Right, so in this case, our medication variable, our independent variable, would be medication versus placebo, and that is, again, categorical. And we would look at a continuous dependent variable of depression score, right? So again, anytime we have one categorical independent variable with two levels, and one continuous dependent variable, that's when we would conduct an independent t-test, right? So there are two really important constraints, right? We have to have one categorical variable with two levels, okay? And no more than two levels, right? So another way of saying that is we have to have a dichotomous categorical, or a categorical independent variable that's dichotomous, or has two groups and only two groups, and one continuous dependent variable. right? So we're always going to be looking for a variable with two levels and a dependent variable that is numeric. Have to get all my pieces in there. So because we are talking about t-tests again, and you guys already have some experience with the Onesample t-test, there are a lot of similarities between the different types of t-tests. So I wanted to make you aware of that. Right, so in a one-sample t-test, what we're doing is we're comparing our sample mean against a hypothesized population mean, right? But this is only applicable in a limited set of circumstances, right? Most of the time, whenever we conduct an inferential statistics test, we're going to have very little information, if any, about the population, right? So in that sense, this test is actually really limited. But let's go ahead and look at the components of the formula, right? So at the top of our little fraction here, we have m minus mu, which represents the difference between the mean in our sample and the hypothesized population mean, right? So this is the actual observed difference between the sample mean and the population mean, right? So that's fairly simple. But on the bottom, it gets a little bit more complicated. On the bottom is the standard error, okay? So at the top is the observed difference, and at the bottom, the standard error represents the difference we would expect by chance alone, right? So it's the difference we would expect, even if there was no true difference between the mean and the population, the sample mean and the population mean, right? So the standard error represents the difference we would expect by random chance alone, right? So if it just so happened, right, that something about our sample, right, something random about our sample caused us to observe a difference, right, that would be standard error. So I think the example I gave you was if you were looking at IQ, right? So suppose you found out through a national survey that most college students have an average IQ of 115, right? Which is above the mean. And you wanted to see whether Mercer students have an IQ that is higher than the national average, right? So you go out into the quad and you are holding a clipboard and you have your intelligence test booklets with you, and you just randomly solicit students from all over campus to take your IQ test, right? And just by random chance, right, Mercer decides to hold a Mensa convention, right? And Mensa is the society for people with extremely, extremely high IQs, like people whose IQs are in the top 10%. And I think it's not just nationally, it's internationally as well. It's around the world. So it just so happens that the students that come by to take your test, right, are obviously really motivated to demonstrate their high IQ. And because they were recently at a Mensa convention, we know automatically that their IQs are higher, right? So the first 10 people that take your IQ test have very, very high IQs. Right? So there's a lot of random chance factors here, right? The Mensa convention is one. Where you were standing, you just so happen to be closer to students attending that, right? Whereas if you took another sample on a different day in a different location, you're likely to not have observed that score, right? So that's what the standard error represents, is just a difference that we would expect by random chance that does not reflect a true difference between the sample mean and the population mean. Okay, so now let's look at the formula for the independent sample t-test. And before I go on to the next slide, I just want to reassure you guys that you do not have to memorize this formula, okay? Because at first glance, this formula can be a little bit intimidating, but you definitely do not have to memorize this formula. Okay, so let's all just take a deep breath and go through this formula piece by piece. Okay, so let's start at the top because it's a lot less intimidating, right? So at the top, just like in the one sample t-test, we're looking at a mean difference, right? So remember, for the one sample, we were looking at the difference between the sample mean and the population mean. But now, for the independent t-test, we're looking at the mean of sample 1, or the difference between the mean of sample 1 and the mean of sample 2, right? And this makes sense because we're literally trying to compare two different groups in our sample, right? It's a between subjects test, so we're looking at the difference in scores or whatever our outcome variable is between sample A and sample B, or sample 1 or group 1 and group 2, right? So that's all we have at the top here, is we have our observed difference in this case in our sample. Just like we had the observed difference between the sample mean and the population mean, now we have the observed difference between group A and group B in our sample, or group 1 and group 2 in our sample. Okay, so M1 minus M2 represents the difference in the sample means between our two groups. Okay, so now let's talk about what's happening in the bottom of our equation, or our fraction. Okay, well, first let's talk about notation. Okay, so here you see df1, df2, df1, df2, right? What does that mean? That means degrees of freedom for each of your groups. So df1 corresponds to the degrees of freedom for group 1 in your sample. df2 represents the degrees of freedom for your group 2 in your sample. Okay? And how you calculate degrees of freedom for this formula is very easy. It's just n minus 1. Okay? So if I had 20 people in group 1 and 20 people in group 2, then my degrees of freedom would be 19. Okay? And similarly, when you see SD1 and SD2, okay, or SD squared 1 and SD squared 2, that's representing the standard deviation for each of the groups in your sample. Okay, so SD squared 1, you literally find the standard deviation for group 1 in your sample, and then you square it. Okay, same thing for SD2. That's standard deviation of your group 2, and you square it. Okay, so one other thing to note is it does not matter which group is designated as group 1 and which group is designated as group 2. Okay, either one, it's entirely up to you which group, whether you want, if you're looking at gender, whether you want group 1 to be males and group 2 to be females, or vice versa, it's fine. If you're looking at extroverts versus introverts, you can have extroverts be group 1 and introverts be group 2. It doesn't matter. They're entirely interchangeable, right? And the last piece of our formula, when you see N1 plus N2 over N1 times N2, that N is going to be your sample size, right? So I just gave you the hypothetical example of your sample of 20 people, right? So your degrees of freedom is 19 and your N is 20 for each of your groups. Okay, again, that's not always the case, it's just an example. Okay, so now that you know what everything in the sample or everything in the bottom part of our fraction there represents, let's talk about what it means, right? So just like with the one sample t-test, right, we had our observed difference between the sample mean and the population mean over the difference we would expect to find by random chance, or the standard error, right? So that's exactly what we have now, right? So we have the observed difference between the mean of group 1 and the mean of group 2, and that whole sort of monstrosity on the bottom is standard error, right? So again, we have the exact same thing. It's just a little bit more complicated because we're looking at two groups in our sample, and each of those groups has some error in it, right? Remember we talked about sampling error? And again, that's just random chance factors that make your sample different from your population, right? So each group in our sample is going to have some error in it. So we need this complicated formula to account for that, okay? But it's all the same thing. It's observed difference between our means over standard error for each of our groups. Okay, so let's look at an example, okay? So let's suppose that we want to answer the question that I posed earlier, which is, do Mercer students have an SAT score that's higher than that observed by obtained by Middle Georgia State students, right? So are Mercer students smarter than MGS students? Do they have a higher SAT score? All right, so let's suppose we have a sample of 15 Mercer students and their average SAT score is 1220 and the standard deviation is 50, okay? And we also have a sample of MGS students with a mean SAT score of 1170 and a standard deviation of 60, okay? So looking at the means, right? The Mercer students have a higher SAT score, 1220 versus 1170, but is this difference significant, right? So does this difference reflect a true difference between Mercer and Middle Georgia State students, or is it just a difference that happened due to random chance, right? So again, our independent variable is college or university, right? So it's categorical with two levels. We have Mercer and MGS students. And our dependent variable is SAT score, which is a continuous variable. Okay, so we know that we're conducting the right test, right? We've satisfied all of our requirements. Okay, so again, our null hypothesis is going to be no difference, right? No group difference. So the mean SAT scores of Mercer students are equal to the mean SAT scores of MGS students, right? The mean SAT scores of Mercer and MGS students are equal or they are not different from each other. The alternative hypothesis is that the mean scores of Mercer students will be higher than the mean scores of MGS students. Okay? All right. So now let's go ahead and plug in our values into our formula, right? And we'll start with the easy one, right? We'll start at the top of our fraction here. We'll call Mercer group 1, right? So we have 1220 minus 1170, okay? And now at the bottom, right, we have our sample size of 15 and 18, right, on the right side of the equation. And then I plugged in 14 for the degrees of freedom for group 1, which is Mercer students, right? So if we have a sample of 15, the degrees of freedom for group 1 is going to be 14, okay? And then we would square the standard deviation for group 1. The standard deviation for Mercer students is 50, okay? And then the second parentheses there, I would have 17 for my sample size, because now we're talking about the sample of MGS students, and we had 18 of those. So 18 minus 1 is 17. And then we would take the standard deviation for group 2 and square it, okay? And then at the bottom, we would add the degrees of freedom for Mercer students, which was 14, and the degrees of freedom for MGS students, which was 17, okay? And then all we have to do is plug in those numbers, okay? And the value that we would get is 2.57, okay? So go ahead and practice this on your own. Go ahead and use your calculator and just make sure that you understand where each of those numbers came from and that you get the appropriate value after you plug in all those numbers. And I would encourage you, if you have one from high school, or if you've already taken Stats 126, which all of you should have, if you have like a graphing calculator or a scientific calculator, anything that allows you to see the numbers that you're inputting, I think that'll make things a lot easier. And certainly there are ways in your calculator to check your work also, which can be helpful. Okay. Okay. So now we know that our obtained t value is 2.57. Okay. What critical value do we compare this to? Okay, so we're going to use our same t-table that we used for Onesample t-test. Okay, so because we have two groups with their own sample sizes, when we calculate the degrees of freedom to find the critical value, okay, we're going to do N1 plus N2 minus 2, okay? So again, we're calculating a separate, we're basically doing the same formula, but we're doing it for both groups, right? So we add up the sample size for group 1 and the sample size for group 2, and we take away 2, right? Just like we would normally do N minus 1. We're doing the exact same thing, except we're doing it for both groups, okay? So in this example, our 2 degrees of freedom for each of the samples were 15 and 18. The respective sample sizes, were 15 and 18, and then we subtract 2, and we get 31, okay? So if we don't have a row in our table that corresponds to 31, then we're going to use the next closest value without going over, okay, which is in this case 29, okay? So our critical value, if we set our alpha level to 0.05, Okay, and keep in mind, right, that because just like with the one sample t-test, we talked about one sample or one, excuse me, just like with the one sample t-test, we talked about one way or one-tailed and two-tailed tests, right? Um, Two-tailed tests were for non-directional hypotheses, where we're saying that the scores in our sample are going to be different, but we don't specify direction, whereas one-tailed t-tests do specify direction, right? So if our research hypothesis is directional, then we would conduct a one-tailed t-test. And if it's non-directional, if we're just positing a difference between the groups without specifying the direction, then we would use a two-tailed test. Okay, so because we're hypothesizing that one group scores will be higher than the other, then we're conducting a one-tailed t-test. Okay, so that means we're going to be working with the last column there where it says 0.05 one-tail, and we're going to go down to 29, and that gives us a critical value of 1.699. Okay, so our t-value is greater than the critical value, and by now you should remember that if our critical value is, if our obtained t-value is greater than the critical value, then we reject the null hypothesis, right? In other words, there is a relationship between college or university affiliation and SAT scores. So Mercer student scores are significantly higher than those of Middle Georgia State students. Okay. All right, so the last thing we have to do is write up our results in APA style. So we're going to start with our hypothesis. We hypothesized that the mean SAT score of Mercer students would be higher than that of Middle Georgia State students. Okay, now we have to report what we found in relation to this hypothesis, right? So consistent with this hypothesis, an independent t-test showed that the average SAT score of Mercer students, okay, and remember we have to include our descriptive statistics, so we have to tell people what the average SAT score of Mercer students was. So we include the mean, and note that the sample M is italicized, right? So we have to tell people that the mean SAT score of Mercer students was 1220, and we also want to include the standard deviation, right? And note that both the sample mean and the standard deviation notation is italicized. Okay, so an independent t-test showed that the average SAT score of Mercer students was higher than the average SAT score of MGS students. And again, we're reporting the mean and standard deviation for that sample. And lastly, we have our t-test, right? So we're going to report, and notice again that the t is italicized. So we're going to report the degrees of freedom, the total degrees of freedom that you use to calculate the critical value in parentheses. And then you're going to report the obtained t statistic. And then you're going to tell us whether the p-value is less than or greater than 0.05. Okay, and one thing I wanted to note, because this is the common question that I get from folks, is how is the procedure different when you're calculating any kind of statistic by hand versus when you're doing it in SPSS? Okay, well, when you're calculating a statistic like the independent sample t-test or any other statistical test that we've done, when you do it by hand, you have to compare your obtained value to a critical critical value in order to determine your p-value, right? So our chart that we just used tells us that if our critical value is greater than our obtained value, the p-value is less than 0.05. If the obtained value is less than the critical value, then the p-value is greater than 0.05, right? But if we're in SPSS, if we're calculating any kind of statistical test in SPSS, we do not need our critical tables, right? We do not need to compare our obtained statistic to a critical value. Instead, SPSS simply tells us what our obtained p-value is, okay? Either way, however, you're still going to report it using this notation, okay? And again, note the italics, guys. So M, S, D, T, and your p-value, or your M, S, D, T, and P are all italicized, okay? And that's just part of the conventions of APA style, okay? All right, so if you have any questions, feel free to reach out, and I look forward to seeing you in my next video.